Welcome to the video on testing the center of a single sample. Here are the general steps, and these steps work essentially for all statistical testing. First question you have to ask is, what is the parametric test that you would like to use? And we ask this question because the parametric test, if you are allowed to use it, is more powerful than the non-parametric tests. You're able to detect a false null hypothesis much better. But all parametric tests have assumptions. So the next question is, what are this test's assumptions? And then you check if the data violate those assumptions. And if the data do not violate the assumptions, then you get to use the parametric test. Otherwise, you have to use the less powerful non-parametric test. So here's the situation. There's a school zone located along Washington Street in front of Will Rogers Elementary School. The speed in the school zone is 20 miles per hour. Here's the question. What is the average, and by average we mean mean, speed that the cars travel in the school zone? Now from experience, my research hypothesis is that the average speed, mu, is going to be greater than 20 miles per hour. That's what the scientist cares about, the research hypothesis. We as statisticians have to create a null hypothesis and the associated alternative hypothesis. If the research hypothesis is greater than, notice that it has no equal part to it. It has to be the alternative hypothesis, because only the null hypothesis has an equals part to it. A greater than or equal to, a less than or equal to, or just plain old equal to. So since the research hypothesis is mu is greater than 20, that's also going to be the alternative hypothesis, which means that our null hypothesis will be less than or equal to 20. Notice how the null hypothesis and the alternative hypothesis divide the world into two possibilities. Either the mu is greater than 20 or it's less than or equal to 20. We're looking at a single sample, although we're going to apply this twice. We're going to look at a single sample. We want to do just a one sample t-test. And the assumption is the assumption of normality. There's also the assumption of independence, but that's tested usually through the data collection process. When we say talk about the normality assumption, what we're actually saying in shorthand is that we are assuming the data are generated from a normal population. So the assumption test is the Shapiro-Wilk test. If the data pass the Shapiro-Wilk test, we'll run the one sample t-test, which is the parametric test. If it fails, then we're going to run the non-parametric test, which is called the Wilcoxon test in this case. So let's begin. First step is to create the folder for our project. Here we are in the Documents Library, Stat Methods. Let's create a brand new folder here. Let's go ahead and call this folder something like School Zone Analysis. Open it. We got to put the data in there. If you want to, we can go ahead and look at the data just as Excel spreadsheet. There's two variables. One is west to east variable, the other is the east to west variable. And if you notice, there is a west to east speed that is just 5 miles per hour. That's going to be a little problematic, or it could be problematic. That's actually the street sweeper that was going 5 miles per hour. But otherwise, the data look pretty good, which is a good thing to see. So let's start up R, set the working directory. For PC people, it's change to dir. Now I got to locate it. Now if you'd like, you can double check that you've got the working directory set correctly by using the getWD function. It's just getWD and then an open and a close parentheses. Hit enter, and it tells you what your current working directory is. And it's school zone analysis, so we did it correctly. Now we open up a script, and we begin our analysis. As always, the first step is to import the data. Since the data is saved in CSV format, we'll use the command read.csv. We have to remember the data file's name, which I don't. So I'm going to go back over to the console window and type in dir open parenthesis close parenthesis. Dir stands for directory. It tells me every file that is currently in the working directory. We only have one file in there, the school zone data.csv. Control C, Control V for paste, and we loaded it. Looks good. Now we can get to know the data a little bit using the summary command. It looks as though, remember our research hypothesis was that mu was greater than 20. Looking at these data, in both cases, mu was equal for the samples, mu was equal to 23.5. So I'm thinking that when all is said and done, we're going to be rejecting our null hypothesis and concluding that the alternative is supported by the data. So let's begin. First thing to do is we're going to look at the west to east group. I'm going to do a box plot of it just to get a feel for what these data look like. And you can see the street sweeper very clearly on there. It's the little dot at the bottom, the outlier. Street sweeper is not really an automobile. I'm not really sure that it's a part of our target population. Therefore, I think we really should get rid of that street sweeper. In order to get rid of something, we need to know its index. To find out its index, one way is just to type in the name of the data set over in the console window, hit enter, and look for its value. West to east, 5 miles per hour, its index is 12. So I'm going to redo the box plot, but I'm going to do it without index number 12. Square bracket, a minus sign, the index, and closing bracket. See how that looks. No outlier. Median still looks to be a little bit higher than 20, because here's 20 miles per hour. Doesn't look like too many of the people were at the speed limit or below. So again, I'm thinking we're eventually going to reject the null hypothesis that mu is less than or equal to 20. But before we get there, we have to determine which test we want to use. We would like to use the one sample t-test because it's more powerful than the non-parametric tests. It assumes normality. Therefore, we're going to use the Shapiro-Wilk test on the data to check for normality. The command is shapiro.test, and it just takes the data. Again, we're going to do it without the street sweeper, so it's dt, which is the data set's name, $, west to east, open bracket, -12, close bracket. Control R. Even without the street sweeper, Shapiro-Wilk test, because the p-value is less than alpha, tells us that the data do not come from a normally distributed population. Since they failed the assumption test, we're going to use the Wilcoxon test. The command for the Wilcoxon test is wilcox.test. It takes the data. Again, we're going to fit it without the street sweeper. We also have to specify the mu naught. The mu naught here is 20 because our alternative hypothesis was mu is greater than 20. And we also have to specify the alternative hypothesis. The options are greater, less than, and two-sided. Two-sided is the default. You'd use two-sided if your null hypothesis was equal. Here, null hypothesis is less than or equal to, so the alternative is greater. Control R. We have some warnings. Wilcoxon test assumes that the data also come from a continuous distribution. In a continuous distribution, the probability of a tie is 0. So it doesn't really know how to do ties correctly. But it can give an approximate p-value, which is what we're going to be looking at. Test statistic is 394. P-value is 6.695 times 10 to the negative sixth. Because the p-value is less than alpha, we again reject the null hypothesis, conclude that the alternative hypothesis better describes the data. The alternative hypothesis is that the true location, otherwise known as the mean, is greater than 20. Therefore, we conclude that the null hypothesis is incorrect, the alternative hypothesis is correct, and that the average speed is greater than 20 miles per hour, which fits with experience. That was all the west to east. Let's do the same thing with the east to west. Again, let's create a box plot, see if there's any outliers. We got outliers both below and above. Both the 16 mile per hour and the 30 mile per hour person were genuine cars. They belong to the target population, therefore we can't get rid of them. I'm not too worried about it affecting the test itself, mainly because you got one above, one below. So we're going to keep everything. Again, recall we would like to use the one sample t-test. The assumption of the one sample t-test is that of normality. That is, the data are generated from a normal distribution. The test of that is the Shapiro-Wilk test. Let's go ahead and perform that. Shapiro.test. The null hypothesis for the Shapiro-Wilk test is that the data are generated from a normal distribution. P-value is greater than alpha. We cannot reject that null hypothesis. Therefore, the data pass the Shapiro-Wilk test. Because the data pass the test, we can use the one sample t-test. Let's do that. Command for one sample t-test is t.test. Takes the data. Have to specify our mu naught. Again, it's 20. Again, specify the alternative. In this case, the alternative is again greater. And Control R. P-value is less than alpha. Test statistic is 6.6708. P-value is less than alpha. Therefore, again, we reject the null hypothesis. Conclude that the alternative hypothesis is correct. The alternative hypothesis is that the true mean is greater than 20 miles per hour, which agrees with the research hypothesis. So those are the tests. There's one other thing I want to bring up here, and that would be the confidence intervals. Let's go back to the west to east part. Confidence interval. To perform a confidence interval for the Wilcoxon test, I'm just going to copy and paste that. I'm going to get rid of the alternative equals greater and the mu equals 20. Now, if I run it just as wilcox.test of the data, it doesn't give me a confidence interval. By default, the Wilcox test will not give confidence intervals. We can force it with conf.int equals true. So this has to be added to the Wilcoxon test in order for R to give you confidence intervals. And here's our confidence interval. 95% confidence interval. Again, make sure you round this correctly. We are 95% sure that the true mean is between 23 and 25.5 miles per hour. Notice that 20 is nowhere in there. Therefore, again, we would reject the null hypothesis that mu equaled 20. t-test is a little bit nicer. Just going to highlight and copy that part. For the east to west, it's just t-test of east to west, Control R. Confidence interval is given down here. For the east to west group, we're 95% confident that the true population mean is between 22.4 and 24.6 miles per hour. So the keys on those is that confidence intervals depend solely on the data, so you don't have to specify a mu naught or an alternative. It's just Wilcox test of the data, and then specify that you want a confidence interval. For the t-test, it only depends on the data, so it's just t.test of the data. That will give you the confidence interval that we want. To do the testing, however, you do need to specify mu naught and the alternative, as long as your null hypothesis is not equal to. If the null hypothesis is equal to, then you don't have to specify the alternative. That's what R assumes you want to do. So what we did here is we actually tested two separate variables to see if they agreed with our hypothesis. Remember, our hypotheses were mu is greater than 20. That would be the research hypothesis, both for the east to west and the west to east. Because it's greater than, that's also going to be the alternative. The null is going to be the opposite of greater than. So our null hypothesis, which is what we're testing, is that mu is less than or equal to 20 miles per hour. And that was the same null hypothesis for both data, the east to west and the west to east. Going through the R script, we first loaded the data, did a box plot, figured out that there was an outlier, and that outlier was the street sweeper who was going only 5 miles per hour. So we removed the outlier, and we kept testing with the outlier, without the outlier. Checked normality using the Shapiro-Wilk test. It failed, so we used the Wilcoxon test, because the Wilcoxon test is the non-parametric alternative to the t-test. We then calculated a confidence interval. Still Wilcox.test, only takes the data and have to specify for the Wilcox test the confidence interval is true. We want the confidence interval. Remember that the Wilcoxon test assumes the data come from a continuous distribution, which means there's no ties. If there are ties, confidence interval and the p-values would both be approximate. Here that wasn't an issue because p-values were very much less than alpha. For the t-test, for the east to west data, passed Shapiro-Wilk test, therefore we could use the t-test. Testing the hypothesis included some additional information. We had to specify mu naught, and we had to specify the alternative since it wasn't not equal to. Confidence interval was a little bit easier, just t-test and then the data. And that's the end. I hope this was helpful.